All right. Last time we talked about counting, combinatorics. We solved a number of problems really quickly. I hope you can work through those problems on your own if they're not already seeming trivial to you. And if you have questions about them, we can discuss those. It would be healthy to discuss them online on the course webpage if you have such questions. Okay, the topic of the day is discrete random variables. This is where we introduce the concept of the random variable for the first time in this class. Okay, so a random variable is a mapping, in other words, a function from the sample space into the space of real numbers. Okay? So what do we have in the sample space? In the sample space, we have outcomes. Okay? Let this be the sample space omega. And in the sample space, we have outcomes W's, right? And we have defined probabilities of outcomes and probabilities for sets, which are subsets of the sample space, sets of outcomes. Okay? Events are sets. Now, we would like to define a function on the sample space which takes numerical values which we can make computations with. Okay, example. Toss a fair six-sided die. Okay, toss a die. There are 6 possible outcomes. It's a fair die, so the probability of each outcome is 1 over 6. Let the random variable x take on the value 1 if the outcome is 6 and 0 otherwise. Okay, so let this be the sample space in the 6-sided die experiment. Okay, the outcomes are 1, 2, 3, 4, 5, and 6. Okay. We define the random variable x in the following way. So x is a function. It's a mapping from the sample space to real numbers, such that x maps the outcome 6 to the value 1. Okay? X is 1 if the outcome is 6. And if the outcome is anything else, okay, let this be set B, okay. On this set, x is 0, okay. So the outcome 6 is mapped to 1, all the rest is mapped to 0, okay. So given that we have defined this random variable, we can define the probability, we can compute the probability that x is equal to 1. What does this mean? We know about, probability is defined in terms of sets. Okay? So is x equals 1 a set? Yes. It's a set of outcomes W such that x of W is 1. And in this example, that set includes only the outcome 6. Okay? So this is the probability of the outcome being 6, which is, by the uniformity of the sample space, of the probability law, that's 1 over 6. Now we can define an arbitrary number of random variables, different random variables, on the same experiment and on the same probability space. So here's another random variable, y. So y maps every outcome to its numerical value. So y of 1 is 1. y of 2 is 2, y of 3 is 3, y of 4 is 4, y of 5 is 5, y of 6 is 6. This is the mapping, this is the random variable y. What is the probability that y takes on the value 1? That is the probability that the outcome is 1. And that is 1 over 6. So the probability that x is 1 and the probability that y is 1 are the same. Okay? In this example. But what is the probability that y is 0? 0, because y does not take the value 0. Okay? X and y are discrete random variables because they take on a discrete set of values. Okay? Rather than a continuous set of values. They take a discrete set of values. Okay, note also that x is a very special random variable. X is 1 if the outcome is 6, which is a set, it could be a set A. X is 0 if the outcome is in A complement. So x indicates whether or not the event A happened. X is an indicator random variable, as we will define later on. Okay, so let's go to the next definition. A discrete random variable, as I said, takes a discrete set of values. Okay? The probability mass function of a discrete random variable is defined as px of x, the function px of x, equals the probability that x, the random variable x, takes on the value script x. Okay, let's write this down. Px of script x. Okay, so I exaggerated kind of the size of the letter x for you to see that this x denotes the name of the random variable. And it's different, it's distinct from this script x, which stands for the value that the random variable takes. Okay? This is defined as the probability that the random variable x takes on the value script x. Okay? It's called the probability mass function. PMF. Okay? So example, find and plot the PMFs of the x and y defined in the previous example. So let's quickly do that. Let's look at the x here. Okay, px of 1 is 1 over 6, right? Px of 0, the probability that x is 0 is what? 5 over 6. And px of script x is 0 for all values of x other than 0 or 1. Okay? This is a characterization of the PMF of our random variable x. Let's plot this. Plot this over here. Let this be script x. So I'm going to plot the PMF as a function of the value script x. Okay? So 0, 1, 2, -1, etc. Because x takes integer values in this example. The probability that x is 1 is 1 over 6. 1 over 6. The probability that x is 0 is 5 over 6. Okay? 5 over 6. So this is a plot of Px of x, the PMF of the random variable x. Let's put that in a box. Okay. This is our first PMF. Any questions? Okay. Let's find and plot the PMF of y then. Okay. Py of y. Py of, if you want, Py of k, how about that? We use k for the value. Py of k, the probability that y takes on the value k is one over 6 for when k is 1 up to 6. 1, 2, 3, 4, 5, 6. And it's 0 for all other values of k. So let's say otherwise. Okay? So Py of k is flat at the value 1 over 6 when k is between 1 and 6, and integer valued. Let's sketch it here. Let me see. So this is Py of k versus k, and the values are all 1 over 6. Okay, 1, 2, 3, 4, 5, 6. The value is fixed at 1 over 6. This is an example. The heights of the bars are all the same. This is an example of a discrete uniform distribution. Okay. So if you look at the random variables x and y, they are both defined on the same sample space. They care about different things, and they give different weight to different things. X cares about getting a 6. The only thing that x measures is whether or not the outcome is 6, whereas y is different. Okay? Now, the support of this distribution is 2. Whereas the support of this distribution is 6. It's spread out over a larger range of values. Do you have a question? No. Okay. Any questions? Okay. So a discrete random variable is completely characterized by its PMF. So once we know the PMF, we can compute everything that we might be interested in about that random variable. We don't need to go back to the sample space description. Okay? And that's very powerful. Okay, we'll elaborate on this, of course, as this course advances. Here's another example. Let M be the maximum of 2 rolls of a fair die. Okay? Find the PMF of M for all M. Okay, let's quickly do this as exercise. Maybe you can, before we begin, you can tell me the support of this random variable M. So in the example, M is the maximum of 2 rolls of a fair die. Huh? Is it a well-defined random variable? A well-defined random variable, what is that? I never told you that. Well, every possible number, every possible value that M can take should correspond to a set in the sample space. Okay, so let's see. What's the support of M? Do you think? How many values does it take? 6 values. Okay. Are they equally weighted? No. Do their probabilities increase with number? Yes. Okay, so let's compute them. Pm of 1 is the probability that the maximum is 1. Well, that happens only if we get the outcome 1, 1. That happens with probability 1 over 36. Pm of 2 corresponds to the set 1, 1, 1, 2, 2, 1. 3 outcomes out of 36 equally likely outcomes, which is 3 over 36. Pm of 3, this time, sorry, I said 1, 1. 2, 2, 2, 1, 1, 2, right? So for the maximum to be 3, why? Okay. For the maximum to be 3, possibilities are 3, 3, 3, 2, 2, 3, 3, 1, 1, 3. 5 possibilities. 5 over 36. For the maximum to be 4, there are 7 possibilities. For the maximum to be 5, there are 9 possibilities. You see the pattern. And for the maximum to be 6, there are 11 possibilities. You can add these to check. Check what? They should add up to 1, right? Why? Because these are the only possible values that this number, the random variable, can take. So the probabilities for these values should add up to 1. Maybe from here we can infer that when you sum a PMF across all values it can take, you should always get 1. Right? Okay, so let's plot this or sketch this. This is 0, this is K, this is PM of, let's use M, PM of M. And the values are increasing from 1 over 36 up to 11 over 36. Okay. Any questions about this? So as you see, the support of this random variable is 6. Its PMF is identically 0 outside this range of 6 values. Okay, so the support is 6. And you can check that the PMF sums to 1, which it should. Okay. So a PMF is a function that takes discrete values, which are between 0 and 1. And these values sum to 1. So if you sum the function overall across the whole range from negative infinity to infinity, you should get 1. Okay. Let's see. What's next? So let's see some special discrete random variables, which are very useful. The first is the Bernoulli random variable, which is probably the most commonly used random variable. So in the rest of the course, we shall define the random variable with the Bernoulli random variable with parameter p as follows. X is Bernoulli with parameter p. If x is 1 or 0, takes the value 1 with probability p and 0 with probability 1 minus p. Okay? We already have a lot of experience with this random variable before even we define the concept of a random variable. Why? Because we worked with coin tosses. Okay? So let's express and sketch the PMF of a Bernoulli P random variable. Okay? So X is Bernoulli with parameter P. This is the notation we will use. X is distributed according to a Bernoulli distribution with parameter P. Okay? What is the PMF of X? Px of 1 is P. Px of 0 is 1 minus P. Okay? So let's plot this. It takes the values 0 and 1 only. The probability of 0 is 1 minus P. 1 minus P may be smaller or bigger than P. But they both live between 0 and 1. Okay? So this is Px of x versus x. Distribution with support 2. Okay? So, despite its simplicity, the Bernoulli random variable is very important. Okay? Since we can describe a lot of generic probabilistic situations that happen to have two outcomes that we care about. Okay? Examples. Indicator function of an event A. Remember, we had an example of a radar trying to decide whether there's an airplane or not. Okay? A could be the event that there's an airplane. A complement would be no airplane. Okay? The random variable x could be the indicator function of A. So x is 1 if A happens. X is 0 if A does not happen. Okay? So similarly, in our first example, x was 1 if the outcome of the die roll is a 6. Okay, suppose you really care about getting a 6. Okay, you're playing backgammon. Okay, and 6 is very valuable. Okay, so x is 1 if the outcome is 6 and x is 0 otherwise. Okay, so then the value of x being 1 indicates that you got 6 or the event A happened. Okay, we call this the indicator function of the event A, and sometimes we denote this as I sub A of W. X of W, let me write this down. X of W is indicator A of W. So let X of W be 1 when W is in A and 0 if W is not in A. Okay? We say X of W is the indicator function of the event A. Okay? So IA of W is 1 if A happens. Meaning the outcome the outcome W is in A. Yes, please. What is a subset? No, indicator function is a random variable. So I'm giving a different name for X. Any other questions? Indicator function is a random variable. It's an example of a Bernoulli random variable. Takes the value 1 with probability P, 0 with probability 1 minus P. Okay, these will be clearer, I think, after we do some more concrete examples. Here's another example. Consider n tosses of a coin. Okay, and when I toss these coins, if I get a head, I'll record it as a success, and if I get tails, I'll record it as a failure, for example. Okay? So let xi be 1 if the ith roll comes up heads. Okay? And let xi be 0 if it comes up tails. Okay? So if the ith roll is heads, xi is 1. Okay? So for each of the xi's are independent Bernoulli random variables. Okay? Why is x, so let's look at x1. x1 is 1 if I got heads, which happened with probability p, and 0 otherwise. So it's a Bernoulli random variable, right? Why are x1 and x2 independent? Because these are, by definition, independent trials. Okay, so these are, the xi's are called a sequence of independent Bernoulli trials. Okay? Later on, we'll characterize this as a Bernoulli process. Okay? It's too early now. Okay? So let Z be the total number of successes in n independent Bernoulli trials. Can you express Z in terms of independent Bernoulli random variables? So there's a certain test that I take. Example, driver's license test. And every time I take it, okay, the probability of passing it is p, okay. And I take this test 3 times. Okay, even if I pass it, I take it again. Okay, for example, I don't know. Maybe this is not very realistic, but I care about the number of times I pass the test out of n times I take it. Okay, so let Z be the number of successes in n trials. It may be hard to think about Z, but if you break it up into all the trials, and you know, since all the trials have the same distribution, suddenly becomes easy to think about Z. So Z is nothing but the sum of xi's, I from 1 to n, where xi is Bernoulli with probability p. Okay? You see this? Z is the number of successes in n trials. So I make 1, 2, 3, 4, up to n trials. In each trial, I get a success or not. Okay? So in this example, these are the successes and these are the failures. I count the number of successes. I can do this counting by adding the results of each xi. Xi is either 1 or 0. So all these 1s and 0s add up to give the total number of successes in n trials. Okay? Okay, good. So what are the possible values that Z can take? 0 to n. Integers from 0 to n. All right. So in a minute, we'll characterize Z as a binomial random variable. But first, I would like to pick up on that driver's license test example. So suppose I have a friend who's trying to pass the driver's license test. And every time he takes the test, his probability of winning, the probability of passing is 25%. And it does not change from attempt to attempt. What he's trying to do is get his license, so he will try until he succeeds for the first time, and then he'll stop taking the test. Okay? I would like to know what is the probability that he takes this test k times, where k is an integer. Okay? First of all, what is the probability that he takes the test just once? 25%, right? Because with 25% probability, he will pass the test at his first attempt. That's it. Okay? What is the probability that he takes the test twice? He has to fail the first test, which happens with probability 3/4, and then he has to pass the second test, which happens with probability 1/4. These events are independent. Okay? So 3/4 times 1/4 is 3/16 is the probability that he makes 2 attempts. Okay? And it goes like this until what? Up to infinity. Okay? It's not guaranteed that the test, this experiment will end. Okay? Potentially, k can go up to infinity. So let's summarize this. Let y be the number of trials up to and including the first success. Okay? What is the probability that y is equal to k? This is the probability that there are k minus 1 failures followed by a success. The probability of a failure is 1 minus p. So 1 minus p to the power k minus 1 times p. Okay? For what values of, which values of k? K bigger than or equal to 1. Let's plot this. Any questions about this? The name is of this distribution is the geometric distribution, and y is a geometric random variable. It takes only positive integer values. Py of k decays geometrically. That's the reason for the name. Py of 1 is just p. Okay, let's put it here. Py of 2 is p times 1 minus p. Py of 3 is p times 1 minus p squared. And it goes geometrically decaying like this, up to infinity. Okay, do you think this sums to 1? Let's verify that this sums to 1. Let's verify this. This is a legitimate PMF. So what are we summing? We're summing k from negative infinity to infinity, py of k. The sum of the whole PMF across all integers. Okay. This is k going from 1 up to infinity, 1 minus p to the k minus 1 times p. But I can write this, I can take p out of the summation, and I can do a change of variables, k prime minus k minus 1. K prime goes from 0 to infinity, 1 minus p to the k prime Okay? And you probably remember the sum of this series when 1 minus p is less than 1. What is the sum of this series? What's your name? No, behind you, Dennis. Sorry. Erdem. What's the sum of this infinite series, Erdem? One over 1 minus p. Okay, this is valid when 1 minus p is less than 1. Okay, so this whole thing is 1. Okay. Any problem here? Okay. Maybe a good idea to give a reminder to you about the sum of a geometric series in general. R to the k. K from A to B. Let's do this together. Huh? What is the result? Of course, R is less than 1 in magnitude. Huh? Are you sure? A and from A up to B. Let's remember. How about this? 1 minus r to the b plus 1 over 1 minus r to the a. Would this work? Let's check. Let's do this. Okay, so what are we trying to do? We're trying to find s, which is r to the a plus r to the a plus 1, all the way up to r to the b. Okay, but r times s is just this thing shifted. B plus 1. Okay, so subtract the 2. Subtract the 2. 1 minus r times s is what? R to the a minus r to the b plus 1. So we're essentially done, right? Let's write the result. S is r to the a minus r to the b plus 1 over 1 minus r. Okay? What was S? S was summation r to the k. K goes from a to b. Okay? So when the upper limit is infinite, r is less than 1, this goes away. Okay? When the lower limit is 0, this becomes 1. So you get 1 over 1 minus r. Okay? So it's community service. Okay. Geometric random variable. We now have derived the PMF of a geometric random variable and have checked that it's a legitimate PMF by summing it across all values and showing that it equals 1. The next thing is thinking about this slightly different random variable. This time, let z be the number of trials up to, but not including, the first success. How is z different from y? Let's check. Number of trials up to, but not including, the first success. So the number of tests that my friend fails before he succeeds. Okay? So z is the number of trials up to, not including, the first success. What do you think? PZ of k. What is the probability that I fail k tests before I succeed, the first one? Well, 1 minus p to the k times p, right? Because I have to fail exactly k tests and have a success at the end. The range of k is, k can be 0 this time because it's possible to not fail at all before getting the first success. So 0, 1, 2, up to infinity. So how is this different from the PMF of y? It starts at 0. The value at 0 is p. The value at 1 is p times 1 minus p, and then p times 1 minus p squared, and so on. The difference is this PMF is a shifted version of the PMF of y. It's shifted to the left exactly by 1 unit. Okay? Any questions? So sometimes in some books, this is defined as a geometric random variable, but in our textbook, the other one, y, is defined as a geometric random variable. Okay, so we'll stick with that definition. Let's see what's next. Okay, so let me give you the handouts for the next part. The next random variable, the next distribution that we will think about is the binomial random variable. Okay. You are already quite familiar with the binomial distribution from last time, because last time we looked at we characterized the probability that I get k successes in n independent trials. Okay? This is the random variable that measures the number of successes in a given number of independent trials. Okay? So let B be the number of successes in n trials, n Bernoulli trials. Okay? So what is the probability? So B is distributed according to a binomial distribution. A binomial distribution has how many parameters? Has the number of trials, n, as a parameter, as well as the probability of success in each trial, p, as a parameter. So it has two parameters. The Bernoulli has how many parameters? 1. The geometric has, again, just 1. This one has 2. Okay? So B is binomial with n and p means B is the number of successes in n independent trials, and PB of k, the PMF, is the probability that there are k successes in n independent trials. What is that? We computed that last time, right? The probability of, for example, k successes followed by n minus k failures is p to the k times 1 minus p to the n minus k. And there are n choose k different orderings for this, which are all equally probable. So together the probability of k successes coming at arbitrary times in n trials is n choose k, p to the k, 1 minus p to the n minus k. for which values of k? K between 0 and n, and k is integer. Okay, all integers from 0 to n. Okay, so we have plots of this. Remember last time we looked at the same plots. Now these are PMFs. Okay, this is the PMF of a binomial random variable with parameters 7 and 1/4. Okay, and this is the PMF of a binomial random variable with parameters 40 and 1/4. Okay, so any questions? Let me repeat. The easiest way of thinking about a binomial random variable B is to think about it in terms of Bernoulli random variables. I from 1 to n. Xi, Bernoulli with parameter p, and it's very important that xi's are independent. Okay? Once you have this down, everything, all the rest will be easy. Okay. The next one is the Poisson random variable. The Poisson random variable is another discrete random variable which is very useful and comes up a lot in a lot of fields. For example, queuing theory, which is a part of, which is a theory that we use a lot in analyzing communication networks and computer networks. The Poisson random variable comes up a lot. And at first sight, its PMF may seem kind of ugly to you. But I promise you that later on, you'll see that it has really nice properties. Okay? Px of k, the probability that x takes the value k, is lambda to the k, where lambda is a parameter, e to the minus lambda divided by k factorial. Okay. So how many parameters do you think this has? 1. Just 1. It may seem tricky, but it has just 1 parameter, lambda. Okay? So it's actually similar to the binomial when you plot it. Its PMF looks like the binomial PMF. In fact, the binomial is a good approximation to the Poisson PMF when we set the parameter lambda to be n times p and make p very small and very large while keeping n times p constant. Then lambda to the k e to the minus lambda over k factorial can be approximated by n choose k, p to the k, 1 minus p to the n minus k, which is a binomial. So anyway, what I'd like you to notice is this is similar to the binomial. The binomial has 2 parameters. The Poisson has only 1. It's lambda. Okay? Let's show that this is a legitimate PMF. First of all, are its values between 0 and 1? Well, they are positive. Okay. Are they between 0 and 1? They seem to decay with k. Lambda to the k over k factorial has a tendency to decay with k. What is its value at 1? Px of 1. Lambda to the 1. I mean, what's that? Its value at 0, first of all. Lambda to the 0, e to the minus lambda over 0 factorial. 0 factorial is 1. So e to the minus lambda. What is its value at 1? e to the minus lambda times lambda. Okay, so depending on whether lambda is bigger than or smaller than 1, that may or may not be bigger than its value at 0. Okay, so let's check that this sums to 1. I want to sum lambda to the k e to the minus lambda over k factorial. K from 0 up to infinity. We'll use a trick. Okay? First of all, this term can go outside the summation because it doesn't depend on k. And then I'll notice something. What is the Taylor series expansion of e to the lambda? Let's expand it around 0 in terms of lambda. E to the 0 is 1. What's its first derivative? Itself. So lambda times first derivative divided by 1 factorial plus lambda squared times the second derivative evaluated at 0, which is 1, divided by 2 factorial, and so on. So we notice that this is nothing but the Taylor series expansion of e to the lambda. E to the lambda times e to the minus lambda makes 1. So we have verified that this PMF sums to 1. Okay, any questions? This is the Poisson PMF, and just at this point, just note that it's a discrete PMF and it's parameterized by only one parameter, which is this lambda. Okay, so let's take a break.